Hello everyone, and glad to do this presentation for our team. Our team is National University of Singapore HLT Group, and my name is Rizet Tao. Here is our author list, and I do this presentation today. So for the active speaker detection, the traditional method is use a short-term method, which means when we get a few seconds of face video, we do a splitting process to get many short segments. Then for each short segment, like 200 milliseconds, we use the audio and visual encoder to get one audio embedding and visual embedding. Then combine these two embedding to a binary classification. The final output is one single ASD score for this short segment to present the information in this very short segment. Later, there is a smoothing method for the final score lists or the score sequence. The problems in this short-term method is can we learn meaningful ASD information from such a short segment? We give an example. Here is a 200 millisecond video segment. We find that it is actually very challenging to know whether she is speaking or not in such limited information, no matter from the audio and the visual. However, for a 2-second video, it is clear to know when she started to speak, when she did not speak. The reason is that for the human, actually we do not judge whether these people is speaking or not based on a very short segment. We judge it based on the internal sentence, a few words. So if you use very short segment, it might not include any words. You cannot do this judgment. So based on that, our model is used to explore long-term feature for the activity detection. We name it TalkNet. That is an end-to-end model. What we did is that we did not use any split process. When we input one video, we feed all the video into the audio and visual encoder to get the final output. So for instance, when we get this video, for the visual part, our visual temporal encoder can get this FV. This FV is a visual feature sequence. The model is learned from the audiovisual speech recognition. And for the audio, similarly, we use a ResNet structure learned from the speaker recognition to get this FA. This FB and FA, they are all the embedding sequence instead of the single embedding, which means the length of this embedding sequence is equal to the number of video frames in this video. The reason is that we have the specific parameter setting in these two encoders. So based on that, we use these two embedding sequence to do the cross attention to learn the modality interaction between these two modalities. And it can also do the modality alignment. After that, in order to learn the temporal information in the whole video, we use a self-attention model. This model is similar to this cross-attention. So the final output is the audio-visual embedding sequence. This sequence has the same length of the number of video frames, which means for each video frame, we extract an audio-visual embedding, and this embedding has learned the information in the whole video, so that can achieve our goal to extract the long-term temporal information. So based on that, we do the final ASD predictions. The final output is the ASD score sequence, video frame by frame. So here is the result. We find that our method can get to 92.3 MAP in the AVA validation set and get 90.8 MAP in the test set. That can improve. That result is better than the state-of-art result. And then we also do some ablation study. Firstly, we learn whether our model can benefit from the long-term information. We keep our model and we change the length of the input videos. If we still use the split process to split all the videos into the short segment, we find that the performance is very worse. And when we increase the number of the input video frames, our result can improve a lot. So that means our TalkNet is actually benefit from the long-term temporal information. That is what we want in this task. And secondly is that whether the cross attention and self attention is useful. When we remove these two parts, the performance will drop. And when we add these two parts, it can increase very obviously. So that means the modality interaction between the audio and visual is important. And to learn the temporal information between the different frames and their interaction is also important. And here, this study, because in this study we use the audio augmentation method. Traditional method usually only do the visual augmentation, but we think the audio augmentation is also important. So the first line is the result without any augmentation, and the second line is the result with the traditional audio augmentation method in speaker recognition, which means you prepare some additional data, some additional noisy data, and add it to the original data to the augmentation. And the last one is our post-active sampling method, which means use the audio in AY data itself as the noisy to the augmentation. That method do not use any additional method. We find that these two augmentation methods are all important to improve the performance. So here are some other issues. Firstly is that our model can train very fast. It only needs 7 hours in one 22G GPU. And apart from that, our model did not use any pre-trained model and did not consider the relationship between the speaker pairs at the same time. The previous study has proved that these two facts can also improve the performance. So we think if we add these 2 points in our model, our improvement can improve further. So that can be used for the future work. And apart from that, we will release the code model and logs for our TalkNet in GitHub next month. The code will include the details of the pre-process for the AVA dataset and the whole training and validation part. Also, we will include a demo script to do active speaker detection for any video, because we know that AVA already provided the face detection method. It has even give the face tracks bounding box. So for the video without that, for the video not in AVA, we need to provide the process like the face detection, screen detection, and face tracking. So for instance, we give a demo for a video not in AVA, and our model can extract who is speaking with the green box and who is not speaking with the red box. Here is the demo.
Have water in your mouth. 2 people have water in their mouths, and one person has to play a bunch of funny videos, and you have to try to like not laugh. And when you laugh, you have to spit it at the other person. So let's just get right into this video.
So in this demo, we can find that there are many noisy and there are multiple faces on the screen. So that's a challenge condition, and our model can also deal with it. So our conclusion in this task is that we found the long-term temporal context is important for active speaker detection, and the modality interaction is also important, and audio augmentation can improve the performance. So that's all. Thanks a lot.
And one person has to play a bunch of funny videos, and you have to try to like not laugh. And when you laugh, you have to spit it at the other person.
Here we broke up. Yeah. Number 4 is how tall are you? Short.
We are starving. We didn't see any celebrities today, but you never know.
On the way out.
We might see.
我也知道英子现在高3了啊，学习压力挺重的。我只是想给他减减压，没有别的意思。
好，我了解了。谢谢。
那个知道，现在，哎，宋茜。
Okay, so in this video, I do some explanation for our code in GitHub to know how to start. Okay, so here is our paper in ICAF. I have already provided. And the first part, this also is unrelated work because I find the information in this part is limited, so I summary it. Like the research paper in AVA and some research reports in AVA. Apart from that, like some research report paper in Columbia ASD dataset. So off this link you can open it and get the full paper, right? And it has 3 parts. The main part has 3 parts. So firstly, you need to install the dependencies. This is installed from a new environment. You can build it like TalkNet, and this is from the existing environment. You just need to install the requirement. I have already write it, and then you can train it in the AVA active speaker dataset. Because in AVA this dataset, I find the download process is not so easy to do, and so I summary it here. You just need to write this part, and this is the path you want to put this dataset, and you just need to do this part and this download. So it will do it end to end, including to download the data and do the pre-process. Okay, you can see here. This code is learned from this project. It's modified based on this project. I just do some summary issue. So when you run it, it firstly will download some CSV files. Some of these CSV files we generate. It's what we generate, so you cannot find it in the website, I think, and you can download it automatically. So after that, it will download the original audio, the original movies. It will take about 6 hours, and it will extract the audios from the movies. It takes 1 hour, and because there are many video clips this dataset has provided, but this dataset only provides some CSV file to let you know which clip we used. So you need to extract these audio clips. This process is very fast, like 3 minutes. And finally, you need to extract the video clips, like the faces. That part take about 2 days. Yes. I did not modify too much based on the original code, but this process is one time, so you only need to do it one time. And if you do not want to do the result in the test set, because test sets do not have the label, so you can only download the training set and the validation set. It will take only 1 day. Okay, so the whole data set has like more than 300 GB, and if you delete the original audio and original video when you get the clips, you only need about 100 GB. And in this process, if you get some warning, you can just ignore it. It will not affect the result. Okay, so this process will do it end to end. After that, you can find the AWA dataset has downloaded in this path, and you can check the structure whether it is correct. And you can do the training. The training is also simple. Just run this line, and you can get the output in this folder. Score means in each epoch I record the performance, like the MAP, the loss, the learning rate. So it will have several lines, and in this part is the saved model, the trained model. I save it in this path. And in this path is the CSV results in the validation set. Okay, so one issue is that in this training process, you do not need to set too many things. I just remain very limited parameters to let you judge. The bench size part, you need to judge it. You need to change it based on your memory size. So, like if you have more than 20 G, you can use this. And if you only has like 11 G, you may need to set it as 1000. It may affect the results, but will not have some bigger decrease. Yes. Okay, so that is the training part. The whole training part is very fast. Each epoch in my GPU, I only use one GPU. I take like 15 minutes, and so the whole training process will less than 25 epoch. So the final time using is less than 7 hours. I think it's very fast. And if you want to use some pre-trained model, we already have trained in this dataset. You can end the evaluation part. So it will download a pre-trained A1 model automatically, and it will evaluate and output this result. You can check whether this is right. Okay. So this model, it performs like 20.8 MAP in the test set. Okay, here I want to explain that how we evaluate our result is to use this get AOI speaker performance. You use this script that organizer provides, but we change a little for some parts. I do not remember. Like this part I changed a lot, a little. So if you want to submit into the AWA server for the test result, you need to delete the first line. Okay. And then for the TalkNet, in
TalkSet and Columbia SD dataset, I want to explain that why we build this dataset. From our paper, we built a dataset named TalkSet because we find that the model we trained in AVA actually can hardly be used for the videos not in the dataset, because AVA has already give you the face bounding box. So if you get another video, you need to provide a face bounding box. This face is not easily obtained by a face detection model because you need to guarantee that the face area you detected is similar to the face area AVA provide. However, we find it is challenging to do that. We cannot really implement very perfectly. So based on that, I built this dataset, TalkSet. TalkSet is built from the LRS2 and LRS3 and Works Level 2, these two datasets. Okay, so when we build in these two datasets to generate this TalkSet, all the faces is detected by S3FD. So when we get some other videos in the wild from YouTube or from other websites, we can only do the same face detection method to extract these face videos and then use our TalkNet to do the active speaker detection. So that can make our model be more useful. So that is our motivation. So based on that, we build this TalkSet. However, the TalkSet is not we build. We just generate from the existing work. So we only provide some file list to tell you that how we generate it, like we use which file in which dataset and what is the label for this file, and this file we use what audio part or visual part to generate this video, like this kind of issue. So we also provide the code that we generated this dataset, but we did not check or ensure it can be used. But when you already has this file list, actually it's not so difficult to generate this dataset. Yes. But we also has provided the pre-trained model that we have trained in the TalkSet. So if you just want to use some active speaker detection model that can be used in some other dataset or for your downstream task, you can just download this pre-trained TalkNet model. You can use it by this way. This is to download this pre-trained model and evaluate in this Columbia dataset. If you do not want to evaluate in this dataset, you can go for this demo part. I will talk it later. So if you do that, you can get our results in the Columbia dataset. This is different from what we argued in the paper, but they are very similar because we train it again. Each time when we train it, get a different result. The whole process, because it needs to download this dataset and do some pre-process, so it will need about 1.5 hours. But it is one time. So after that, you can only do the active speaker detection. It will take several minutes. Okay. So this is the path you want to save the Columbia dataset. So this part is the last part is more interesting. Is that if you only want to extract the speaking part, you only want to extract the active speaker detection video, how can you do? I provide a demo for you. This demo is end-to-end. You input a raw video. This raw video can be any format like MP4 or AVI. And then you put it in this demo folder. You can name it like the 001. And then you do this line. Or you only need to set to tell the code that which video you want to use. And then it will download this pre-trained model in TalkSet automatically, and it will get the output. The output has this structure. The final output for visualization is this video out AVI file. That is, in this file, I have marked the active speaker detection, the active speaker by the green box, and the non-active speaker by the red box. And here is some like the detected face crops, the video frames, and some face detection, screaming detection, active speaker detection, and the face tracking result. I all saved it here. And this is learned from this project. Okay. So after that, you can get the result from end to end. Okay. So if you find our paper is or our code is useful, you can cite our paper or start this project. Okay, first start for this project. And also I summarize some FAQs here. that is the question that I think you may meet in the process. So you can check it if you meet some problem. Or if you if you have any question, you can use the issue part to ask me or send an email to me. Okay. To summarize this work, I think it's not a very big work or it's very novelty. It's not very novelty, it's just a common work. But I think it's useful, and I try my best to summarize the code to make it can be easily used by all the users, and I hope it can assist the community to improve. Okay, so if you have anything that you think I can further improve this project, you can please let me know. Okay, so that's all. Thank you.